Welcome to our presentation. This is a student-proposed project. I'm Nathaniel Valant.
I'm June. I'm the client of this project.
My name is Eli Eggers.
I'm Nathan London.
I'm Trevor Buck.
And our advisor is Dr. Philip Jones. The goal of this project was to design a system that can autonomously monitor certain conditions in a field that can affect the growth of crops and then relay that information to the user. The sensors we picked at the suggestion of our last advisor are soil moisture, air quality, temperature, pressure, and humidity. The method we took to meet this goal was by designing a network of microcontrollers that drive sensors and wireless communication to a central server. The method we use for wireless communication is called low range, or LoRa. This will be expanded on later in the presentation, but it's a method for broadcasting information that's slower than other methods, but it's low power and offers a longer range compared to options like Wi-Fi or Bluetooth. And then we use commercial off-the-shelf sensors to reduce cost. So some of the major requirements to carry out this design, we focus them into specific categories so we could focus our efforts. The main categories are cost, wireless communication, and longevity. For cost, we aim to make these beacons under $100 in materials. And then we achieve this by using commercially available sensors and 3D printed casings, which provide cheap custom casings for our designs. The goals we were trying to meet for wireless communication are 2 miles of wireless communication range and autonomous communication between both beacon and receiver and beacon to beacon. This would provide a method of scaling up the range of the beacons by allowing beacons to use other beacons to reach the central server. Lastly, we focused on longevity to reduce user input once the system was installed. We tried to make the system both resilient and power efficient. We achieved this by using solar charging batteries and panels and a custom PCB, as well as 3D casing to protect the circuits.
When it comes to the receiver, we designed a housing box 3D printed that would hold a Raspberry Pi and a LoRa module. This Raspberry Pi would take in the data, then use the data to append .txt and CSV files that would then later be used as an HTML for a website as a server, as the Raspberry Pi would host a server. When collecting the data, there was 2 different ways of storing data. We stored it as TXT and CSV. These files were created both on the desktop and in the www folder. This was so that we could allow the user to both access it through their phone if they wanted to, or allowing them to take the receiver into the field and allow them to monitor their stuff when disconnected from the internet.
So for the beacon, we had to have a radio, microcontroller, and sensors, and then a power source. For the microcontroller, we chose STM32. For the radio, we chose a LoRa module, which is, as said earlier, very low power and long range. We chose a bunch of different sensors for collecting data, and then we had to figure out what power source we wanted to use. And we decided to use a solar panel and lithium-ion batteries. So for the STM32, we chose that as the main microcontroller, mainly because of familiarity, because we've worked on that before, but also because they have so many different variants that it's hard to not be able to find something that they have. Their Nucleo L specifically is for low power, and in our testing it only consumed about 16 milliamps while running at 80 megahertz. And it's also very easy to integrate these microcontrollers into custom PCBs. So we used off-the-shelf components for cost effectiveness. We chose the BME 680 temperature, humidity, pressure, air quality sensor. It doesn't use very much power, and we interface it with I2C. Then for the soil moisture, we use the SEN0114 sensor. It's a resistive sensor, so it basically measures the resistance of the soil to get the moisture. And then the power supply, we chose to use a small 12 volt, 5 watt solar panel. We chose that because it was enough to give us the power that we need, but it's also pretty small and not very expensive. We chose the BQ25185 power regulator and solar charger. That chip is smart, and you are able to supply it power, and it charges the batteries. Because lithium batteries, they have to be charged. You can't just apply voltage to it. You have to do it smarter than that. And for the batteries, we chose 2 lithium-ion 4.2 volt batteries that are 3,300 milliamp hours each. For the LoRa, we chose pre-built modules mainly because it simplified the interaction that we had to do with it. The many modules will use SPI for communication. This one just uses UART, and it's transparent, so all you have to do is write to it, and it will just transmit. You don't have to do any extra overhead that's carried by the module itself. You can see here our packet structure. We decided to fit all that into one packet: the temperature, pressure, humidity, air quality, soil, and then an error bit, and also the battery voltage and the ID of the beacon. And you can see the approximate range is 5 kilometers or 3 miles. And this is configurable depending on the bandwidth that you set and other parameters. So for the PCB, this is the PCB for the beacon itself. The goal of the PCB was to integrate all the parts together so that we didn't have to have separate modules, because separate modules cost more, they use more power. This PCB has the STM32 on it. It has the solar charger